So let's review quickly the kinematics quantities, their definitions, if there is an equation. The famous kinematics equations, the rearranged one. We won't go through how we get them, just so that we remember which one are they. I hope you use them a lot in grade 11. And the graphical representation, how certain types of motion will look like. All right, so let's start with quantities. What I try to do always is make a table. So we start from the very basic one, which is position. So I put it here. Position, it's a vector quantity, so I put a V. Actually, I'm going to confuse you with, so I'm going to do this. It's a vector. The variable that we use in this course is D, and usually we care about initial and final position of a motion. All right. Of course, in two-dimensional world, we're going to have the components. All right. So we remember how to get components now. Then we have a displacement. All right, and the displacement is defined as the difference or the rate of change, the change in position. So final quantity minus initial quantity. So here's an example of subtracting vectors, by the way. In component form, again, this is a vector. And the units are meters, right? The SI units. In a component form, we would write it as delta dx equal to dfx minus d ix, and delta dy equal to dfy minus diy, right? And we move on. So we have distance traveled. It's a scalar. It's still measured in meters. And the distance is always greater than or equal to the magnitude of displacement, right? To give an example, if you have something going 10 meters to the right and then 10 meters or 5 meters to the left, this is delta dt, right? However, the distance traveled is the length of the path, right? But the displacement is just the magnitude of that little vector there. So I'm hoping you remember this inequality here. Then we have rates of change, right? So the first one is average velocity. It's a vector, and the units are meters per second, and average velocity is defined as the rate of change of displacement over time. All right, the same idea. I'm going to use a curly bracket from now on. The x component is going to be delta dx over delta t, and the y component is going to be delta dy over delta t in case we're in a two-dimensional world. By the way, guess what happened if we work in 3 dimensions? We just add the z component as well, but in grade 12 physics we won't do that. You may do that in calculus though. Once we define average velocity, we have average speed. We won't use it much, but it's nice to know. It's a scalar quantity. The units are still meters per second. However, average speed is the ratio of the distance traveled over time. All right, and there's no need to talk about components here. We move over to instantaneous. So far, this one here are average things, right? So now we need to know what happened in an instant, right? So first we define what is an instant. An instant is a time interval at a particular point, time interval that is very small. How small? As small as it can be. So what is the smallest is something that approaches zero, but it can never become zero. Scientifically, actually, an instant can never be zero, right? We go into quantum world if we talk about that. So having hopefully understood that, then we go to instantaneous velocity. Again, it's a vector, and the units are meters per second. So instantaneous velocity is defined as average velocity for a very short time interval at a given point, right? So how we write that is the limit when the time interval is approaching zero of the average velocity, which is delta d over delta t, right? Graphically, in grade 11, you mentioned that this is the slope of the tangent on a dt graph, all right? We're gonna quickly go through that. The same idea, we have Vix is, actually I'm not gonna go into the limits, but we break it into components because we deal with initial and final velocities usually. So we have Vix and Viy, Vfx and Vfy in 2 dimensions, in anything with 2 dimensions. Obviously there will be a change in velocity, so we talk about acceleration. Again, it's a vector, and the units are meters per second or meters per second squared. So the definition of the acceleration is the change in velocity over time. So it's a rate of change, all right? Or we can write it as Vf minus Vi over delta t. All right, and the same idea, we can talk about Ax and Ay components in 2 dimensions. All right, so now let's put the, so these are the definitions. So I'm going to write the equations where we, so this is one, right, the average velocity, and this is the other, the acceleration. And we manipulate them. So we're going to talk about types of motions. Now that we have all our quantities, and they are uniform motion, I use the acronym UM, and what does mean uniform motion? That velocity is constant throughout the motion. All right, not speed, velocity. We have a uniform accelerated motion. I use the acronym UAM. In here, the acceleration is constant, not the velocity, all right? Not the speed, the acceleration. And these are in 1D, and of course we have the motion in 2D, and the one that we use the most is projectile motion, I use PM. In here, the x component velocity acceleration, sorry, is 0. The y component is constant, non-zero. Right? So gravity, for example, two-dimensional motion of a projectile, an object in under the influence of gravity only, or the motion of an electron in an electric field, and so on and so forth. All right. A special one that we deal a lot with, and it's easy to work. It's a great example of. It's a free-falling motion, example of uniform accelerated motion, free-falling motion. I use the acronym FFM, and in here, the acceleration is actually the acceleration due to gravity. On Earth is 9.8 meters per second squared. So here on Earth, near the surface, obviously, the acceleration is 9.8 meters per second squared down. Of course, you can round it to 10 if you will, all right, as long as you state it on your problem solving. So these are the types of motions. Now, if acceleration is constant, then it's safe to assume that average velocity is actually the midpoint of the velocity. So it's vi plus vf over 2. So remember, only if the acceleration is constant, then you can use this. So here is one equation. Then I'm going to write the other one. So the other one is a rearrangement of the definition of the acceleration, which is vf equal to vi plus acceleration times time, right? That's right, 2. Then we have, from the definition of average velocity, delta d equal to vi plus vf divided by 2 times time. This is nothing but using, instead of average velocity, using the midpoint vi plus vf over 2. And then once you manipulate these two, you get the other equation that you've been using in grade 11, which is vi times delta t plus half of acceleration times time squared. So remember, equation 4 is a combination of 2 and 3. You can try it if you want at home. Then the other one is, again, the combination of the previous 2 and 3. Vf delta t minus half of a delta t squared. And the last one is that a combination of the 3 and 4 or 3 and 5, that vf squared is equal to vi squared plus 2 times acceleration times displacement. All right, so these are the equations that we're going to rely on, whether it is 1D or 2D. All right, guess what happened if it's in 2 dimensions? We just add the subscript x or y for each of the vector quantities. I'm going to write here, these are vector equations, very important. All right, and they are true only if acceleration is constant. All right. So next, I'm just going to introduce you the graphs very quickly, and what information we find from each graph and how. It's just a summary, and then we'll do an example of graphs.